The dot product is a mathematical function that occurs when you're trying to basically multiply two vectors. There's actually two ways of combining vectors together. One is the dot product, which is also called the scalar product because it creates a scalar. The other option is the cross product, which we are not dealing with right now. So this is, in a way, the idea of projecting A onto B and then multiplying the two together. Mathematically, this is one way to write it, that A vector dot B vector, these must be vectors, this doesn't have meaning otherwise, is the magnitude of A times the magnitude of B with cosine the angle in between them. And this picture, that angle is called alpha. Obviously, it could be called theta. That's just a question of variable name. So this is one of the definitions of what the dot product is. It's a little more tricky if these are three-dimensional vectors. So right now we're just going to worry about vectors in a plane. So what you need to then think about is for different categories of angle, what type of dot products you get. If A and B are perfectly parallel, cosine of 0 is 1. This means that A dot B, when they're perfectly parallel, is just the magnitude of each of them multiplied by one another. If there is an angle smaller than 90 degrees, you have a positive dot product. And if your angle is exactly to 90 degrees, you have a 0 dot product. If they are almost perfectly anti-parallel, such that the angle is greater than 90 degrees, but not exactly equal to 180, you actually have a negative dot product. This is very important. And if they are perfectly anti-parallel, then it's actually the negative case of this first one, where you have negative magnitude of A times the magnitude of B. So do remember that when we write A and B like this, we're meaning magnitudes, that you're not going to bring any signs over. So this is one way to deal with dot products when what you're actually working with is the angle between them. There is a second definition of a dot product where you use the component form. The book goes through the derivation of how you get here. I won't ask you to do that, but hopefully you can either follow the derivation in the book, or maybe this is something you've seen in a math class before. And something to keep in mind is that whenever you have 90 degrees between two vectors, their dot product is 0. So what the derivation to get here depends on is that the unit vector in the x direction and the unit vector in the y direction are perpendicular, so the dot product between them is 0. So remember that I can write a vector as its component with a unit vector, and you can use either I hat or you can use j hat, as the book does. I hat, j hat, or x hat, y hat. And so if you write each vector this way, then to do the dot product, you just are multiplying each value together for A and B, and then you're adding them. Here, you are actually going to have signs appear. So for instance, AX can be a positive value or a negative value. So this is actually equivalent to the previous definition, but a different way of writing it. So two quick examples to show you how to use these two. These are simple equations to plug values into. You're going to choose which form to use based on the information that you have. In this first situation, you know the magnitude of each of the vectors and the angle in between them. So it makes the most sense to use the AB cos alpha version, where you're using the magnitude of each of these, 3 and 4, and then cosine of the angle in between them. You multiply that out, you get 10.4. In the second situation, you aren't explicitly told the angle between them, and you are not explicitly told the magnitude of each vector. Obviously, you could calculate it out, but once you're giving the vectors like this, you can simply get what the component values of each of them are. You simply use the coordinate system provided to get what the x component and y component of A is, the x component and y component of B. You then multiply them out. Note that the y component of B is -1, and you do actually put a -1 there. You don't just put 1. So that means that it's 3 times 4, which is 12, plus -3, so your total is 9. So each of these are just based, the choice you're making for equation is based on the information that you're provided. In an actual physics situation, You might use either one based on what you think is easier to get to. You'll have to infer based on the geometry of the situation what the angle is, or you might have enough information to know what the component values are. The reason we are talking about this right now is because we need to calculate work. And work is going to depend on a specific force and a displacement, where both of those are vectors. So normally we're going to be using the first version of our dot product, where we take the magnitude of the force, again, no sign, no directional information, times the magnitude of the displacement, where again, that's just the distance, and then we multiply by the angle in between. There might be situations where you actually know your x and y components. Perhaps that's a perpendicular and a parallel component, and then you can use this form. So this is valid, but typically going to be less useful than this version.